Oh, yeah. Period.
All right, let's take a look, guys. Let's, let's take a look at our daily routine, current work. Here are the gas stoichiometry answers. And then you are to basically go through the review. I'll answer any questions on the review on Thursday. And then we're going to test on Friday. Those of you that are here live, you have the option of waiting until after school that day or testing on Saturday. And you can use that time to review. Totally up to you on that. So that is the week. Any questions? So basically the stoichiometry was the only new material. Olivia, did that email I sent you make sense?
Yeah.
Yep. That's why ammonium nitrate is such a great explosive, because it has the ability to make all of those moles of gases. And remember, it doesn't matter what kind of gas you're making. It's about the number of moles that determine the volume and pressure at any given particular temperature.
Could we go through number 3? I couldn't figure out how to do it.
Yep. Let me grab a copy of it. It's blank, hopefully. Hey, Johnny. All right, let's go to the visualizer. All right, so the question that was asked about was number 3. So we have ammonium nitrate. It's an explosive that undergoes decomposition. For every 2 moles of it, you get 4 moles of water, vapor gas, 1 mole of oxygen, and 2 moles of nitrogen gas. So if 10 grams of this undergoes an explosion, every 1 mole of it is 14.01 times 2 plus 16 times 3 plus 4.04.
The answer is 80.06.
Is 80.06 grams. And every 2 moles of it make 4 plus 1 plus 2 moles of gas. And Gavin, that's the trick on this one. 4 plus 1 is 5, plus 2 is 7 moles. It does not matter what gas we're making. We're just making moles of gas. Ten times 7 divided by 2 divided by 80.06.
That would be about 0.4371.
So 0.4372 moles of gas. We want liters. So if PV equals nRT, V equals nRT over P. That's 298.15. So we're going to take this moles. Since we have atmospheres, our R is going to be 0.0821. The temperature is in Kelvin. 0.4372 times 298.15 times 0.0821 divided by 1.
It's about 10.7018.
10.7 liters. Gavin, does that make sense?
Wouldn't it be 0.437 because sig figs? Or am I like doing
Yeah,
that?
I always, since I know that's not my final answer, the 10.7 is, I always go out extra here and plug those into the equation. I do all my rounding at the end.
Okay.
Gavin, you good?
Yeah, that helped. Thank you.
You're welcome. Which one do you want to see? Question number 5 was asked about. Oh, dang it. This is the one that what's his butt wants to see too. Why can't I remember that kid? Davis Olson? Is that a kid? Yeah. Yeah, we can do it. He'll probably end up figuring it out. Actually, he can watch the Zoom and figure it out. Haha, David. Haha. So if we take a look, LiOH, we have 1 gram of this. That's probably all you needed to start out, right? So we start off with 1 gram of LiOH. (6.94 plus 16 plus 1.01).
The answer is 23.95.
Every 23.95 grams is 1 mole. Every 2 moles of LiOH is 1 mole of CO2. One divided by 23.95 divided by 2.
The answer is about 0.02087.
Again, I'm going out extra digits because one of these things is going to end up determining my significant digits. It would be that 1 atmosphere, but I'm assuming that's 1.00. So I'm going to have probably about 3 or 4 significant digits at the end. This thing isn't, like this worksheet doesn't seem to care about significant digits. That's not what's being tested here. So that's why they put stuff like 1 atmosphere in there. All right. 22 plus 273.15.
It's 295.15.
So again, we are looking for volume. So V equals nRT over P. 0.020877 times 0.0821 times 295.15 divided by 1.
It's about 0.5058.
0.5058, which will round to 506. Yeah. Yeah, I mean, that's the thing. On a testing situation, usually it's set up for sig figs. Whoever designed this worksheet didn't care about them. You know what I mean? Usually I try to correct things so that they have about 3. You're welcome. This is basically just practice for the story.
Can you go through?
For you?
Oh, I'm sorry.
No worries at all.
Go ahead, Raylan.
You what? Well, it's because they didn't say 1 gram, they put per gram. And then that's whenever you have to say, oh, what does that mean? That means 1 gram, right? So it's trickery. Dun, dun, dun. Raylan, what were you saying?
I was just gonna ask if you could go through number 6 as well.
Sure. So a 3.31 gram sample of lead nitrate with its molar mass of that is heated in an empty cylinder where the volume of that, the salt decomposes when heated, according to this equation. Assume complete decomposition. What is the pressure in the cylinder after decomposition? Assuming that PbO takes up no volume. So that means we have 2 gases. So what are we going to do to those number of moles?
Add them.
You got it. So if we start with 3.31 grams, every 331 grams is 1 mole. Every 2 moles of PbNO32 is 5 moles of gas. (3.31) divided by 331 times 5 divided by 2.
It's 0.025.
Again, we are looking for pressure this time. So P equals nRT over V. 0.250 times 0.0821 times 300K divided by 1.62.
I can't get the answer to that on Apple Watch.
You're a liar. Ah, I said 300K. 0.250 times 0.0821 times 300 divided by 1.62.
It's about 3.8009.
She didn't hear me say 0.025, so it is 0.3809, which is atmospheres. Was it the 5 moles that got you?
Yeah.
Yeah, right. That's the
When
trickiness.
do you know to only the gas moles?
It doesn't say anything about what is the pressure of the NO2, or it doesn't say, anything about a specific thing on this one. It just says, what is the pressure after complete decomposition? Same thing with this one right here. It says, how many liters of gas? It doesn't say how many liters of O2. It doesn't say how many liters of N2. This one,
So when it's a problem like that, you just add the coefficients?
yeah, you add up all the coefficients of the gases. Note that we did not add in the 2 PBO on this one. Is this one where we add them? Oh, no. See, this one specifically says that the carbon dioxide is isolated from all other gases. So we're only doing the carbon dioxide here, right? It'd be the heck of a question is if they gave you this information and they said, what if the total pressure was this, what's the pressure of the H2O then? Well, then you would have to do for every 7 moles of gas, the total pressure, you'd have to do that ratio thing that we did before. Probably not going to do that. The drain cleaner one only finds hydrogen gas. All right. So what I would work on for you is the review for the gas law problems. I'm going to see about getting another conceptual review put on there as well. It kind of has the conceptual things because these are all just math again. So I want you to realize that this test is not just math. There is like conceptual things that say like, oh, if pressure goes up and temperature stays constant, what has to have happened to volume? Right? So you'd have had to say volume goes down, that type of thing. Questions there? All right, I'm going to do a couple reactions that produce gases actually. Yesterday, did we do the can? Yeah, so yesterday you guys saw the can where we increased the pressure in that can and caused it to explode. Today I'm going to do a combustion reaction with methanol, and I want you to think about the just basically why what happens. So I'm going to have to switch out of this and move to the other one. So I'm muting this one. Can you hear me on this one? Do I have to share on this one? Speaker view, and that's what makes this one big, right? Cool. So you guys know better about that than me. Oh, I can feel my back hurting a little bit. Been standing up too much lately. So let's try this again. Has anybody ever seen that British comedy show, The Web and something? Like this guy's like, funny. All right. So you can see my hand here. Good. You can see this here. Good. So what I have here is a plastic bottle. Sounds like there's something in there. There is. Now there isn't. Make sure I've got some matchers. This is methanol. So I'm going to pour about 20 milliliters of methanol in here. I'm mixing it around. Maybe I can do like a methanol dance. Nope. What I'm going to do is methanol, the formula is CH3OH. I'm going to add oxygen to that. You can balance that equation if you want. I'm going to move everything that could possibly break away from it. Afterwards, I'll show you a video of where this goes completely wrong. I need some finger extenders so I don't burn my fingers off. Hopefully this isn't a video of this going completely wrong. So you can see that the fire is still reacting. Anybody want to explain why it does that heartbeat type of thing?
Because the oxygen has to keep going through the small opening to continue reacting.
Very good. Both answers are correct. What's your name? Ian. Ian and Dawson, that's exactly correct. As it initially goes, there's oxygen in here, right? So it can actually react and combust to what we would call complete combustion. As it starts to do that pulsating thing, it's drawing oxygen from the top. And that's why it kind of pulsates until it actually all goes out. Now we know in the room, oxygen is in excess. But in order to keep that flame going, just like we saw this yesterday, if that flame dies out and no more oxygen comes in, that means that we have unreacted methanol in here, right? Yeah. And the carbon dioxide is lighter than or heavier than the air? More or less dense? More dense, right? So it could be sitting in here. Well, let's check. What's a way that I can test to see if I have excess methanol in here? Light it on fire. So remember that this produces H2O and CO2. So some of that right there may be recondensed H2O. But a lot of that right there could be methanol. Now just for fun, let's do something. Just for fun, let's put some lithium nitrate in here. So what lithium nitrate is going to do is it's going to free up these lithium ions. And these lithium ions, whenever they get excited, they emit a beautiful color. You'll see it hopefully. I don't know how well the camera will show this. Can you see my hand? No? I can't even see my hand. I need light. Let me see. Yes. And you can see that definitely there was some ethanol in there. Now, what color is lithium when it burns? Yeah, it's a very scarlety red. Unfortunately, I'm not sure if the camera is able to pick that up, but it's a very beautiful color. Somebody asked me earlier today what my favorite color was. I don't know, this is pretty close. You know, I told them blue because it's like the sky or whatever, but I don't know, maybe this beats it. So we know that there was some excess in there. That means that there wasn't enough oxygen that got in there to give us complete combustion of that. Cool. Any questions from those of you at home? All right, so you guys have that review to go through. Now I got to think, how many of you are coming in tomorrow? Give me a thumbs up if you're coming in tomorrow. So we got, oh, that's right, Olivia Gammon, and okay, cool. Nobody else. All right. So I'll have to think of some type of cool demonstration for you guys to do for these guys. Maybe we'll do the combustion of hydrogen. So we'll see you guys until tomorrow. If you have any questions, hop back on the Zoom. It'll be open. Bye. Cool. And if you guys have any questions, obviously just raise your hand.
So can we make like how you put all the lithium, or not lithium, right? What you put in the bottle again?
Methanol.
Methanol. If you put a bunch of methanol in a bottle, turn it upside down, hold it on fire, use it like a rocket.
The problem is that the methanol is volatile, which means it vaporizes quickly. But the problem is that it's going to leak out. I bet that you can find somebody that's done it though, and they've just done it real quick or something, right? So if you look online, you might be able to find somebody that's done it real quick. It usually creates water vapor, but since it was sitting in there, it was able to liquefy. So that's why you can still see a little bit of water on that desk. Blake, Ben, do you guys have any questions at all? I'm going to have to close this room out so I can get the Zoom recording. Ben?
No, I was just.
All right, cool.
taking one.
I'll talk to you guys later. Have a great day.